students. This is Mr. Mbulamuko Isaac from Namgongo Secondary and Vocational School. Today we are going to look at submath, and in particular we are going to look at depreciation. So under depreciation we are going to look at some few things in this session. We have the objectives on our screen, and by the end of this session you should be able to know what depreciation is. If someone asks you, what do you understand by depreciation, you should be able to explain what depreciation is. Secondly, we should be able to know the basic starting general form of depreciation. When we are to depreciate, what do we do? That we should be able to know by the end of this lesson. Another objective we have there is to know how to depreciate different functions and a constant as well. So these functions could be in addition, difference, division, or subtraction. We should be able to look at them all. And then finally, we should be able to calculate some few numbers that are dealing with depreciation in areas of addition, subtraction, and division and multiplication. Yes, to start off now, since you said we need to know what depreciation is, what would someone call depreciation? Now, depreciation, when we are defining it in math, we define it as the gradient of the curve. Now, when you talk of a gradient, someone will still ask you, what is a gradient? For example, if I sketched my axes, I have my vertical axis and my horizontal axis. So this is the x-axis and this is the y-axis. We have these two. Assuming we have a curve, if we have a curve of that nature, and then we want to get its gradient, this we are going to use depreciation, and this is why we are saying for us to define depreciation, we define it as the gradient of a curve. Now, in gradient, when you're getting gradient, you remember in your level we looked at gradient, and gradient of any given line is the difference in the change of the y-axis divided by the difference change of the x-axis. So in other words, we have this line cutting or passing through a point on a curve. So if we dot off and we form what we call our slope, we shall have that from here up to here we have had a change in the x-axis. Then from here up to a given point here, we have had our change in the y. So when we want to get the slope of this curve, we get its gradient, and that is simply what we put as depreciation. So in our math, it is normally read as the y, the x, or what we call depreciation of the function y with respect to x. This is what we call depreciation. So whenever you find the y dx, we are depreciating, or that is what we call a differential function that has been depreciated. Now, to move on, we also have the general form. We have the general form, which we've talked about. We have the general form, and in our general form, we are going to consider a given function a x to the power n. We can consider a given function y, which is equal to ax to the power n. Now when you look at your slide, you can maybe these letters where a, comma, and n are constants. They are constants. So these are numbers, and our only changing variable is x. And we have a function y. Is it okay? Now, in this form, simply put, whenever we are differentiating, the first thing you note is we reduce the power by 1. We reduce the power by 1 for that power there. And at the same time, we shall multiply our function in bracket, this is the ax power n, with the initial power, which was our what? Our n. So this means that we are going to have something like this. When we differentiate our y, we shall have dy dx, because we've said whenever we talk about differentiating a function of y with a given changing variable of x, we get the derivative of y with respect to x. And on the right hand side, we shall implement these two steps. We can start by multiplying by the initial, or you can start by reducing the power, provided you do these two steps. So I will say we get the initial power, which is n, times our function ax, and we shall reduce that power by 1. So this is what we shall get, and this is the general form of how we can differentiate in a given function. Okay, now from here we can then look at some examples. Applying this simple knowledge that we have learned. On the screen we have examples, and they are telling us differentiate the following with respect to x. So you have Roman number 1 there. Our Roman number 1, we have those examples. We have Roman number 1, which is having x to the power 8. They are telling us to differentiate these with respect to x. So remember, we started by saying it is always a function. Now someone will ask me, where is the y? Y may not be given in some cases. So what shall we do? We first introduce it by letting. So you will let y or any other letter, depending on what you want. But the common letter we will find in textbooks is y. We can let y equal to x the power y. Is it okay? Now we have introduced this function. Then we can go on to differentiate it with our knowledge we've learned. So when we differentiate the left hand side, we shall have, when you differentiate y, we shall get the derivative of y with respect to what is changing. And what is changing? It is our x. It's going to be equal to, we say you multiply, so you bring this power and multiply it with this function. So we shall have 8 times, and then you will get the power of that function and reduce it by 1. So what do we get? We shall have, therefore, 8x, 8 minus 1 we get 7. And therefore that will be our answer for dy dx as required. That is the first example. As simple as it is. Then we can move on the next example. On the next example, we have Roman number 2. Still on the same example, we have Roman number 2, which is saying differentiate this function with respect to x. Since we've learned that whenever we are given a function of a given variable and you don't have the y, you can first start by letting. Now, another way you can say, since they want us to differentiate all of this, then we can just differentiate it directly. So we shall say that the derivative of where we would have put our y, we shall put that in function of 3x to the power 5 with respect to x is going to be equal to, then we continue. So I've said the derivative of this function, I put it here, with respect to x will equal to, I repeat the same process. We have 3 as a constant here, but remember we said we multiply by the power first. So we shall multiply 3 with 5 and then multiply it as well with x the power 5 minus 1. So brackets are better sometimes, not to confuse yourself, so learn how to use them. So when we continue, this gives us 15, it will give us 15 x to the power 4. 15 x to the power 4, and that will be our answer for this value. So you can come down and say, therefore, the derivative of 3x to the power 5 with respect to x is equal to 15 x to the power 4, and that will be our answer there. That will be our answer there. Okay, let's continue with the next Roman numeral. Let's continue with the next Roman numeral. We have Roman numeral 3. I purposely chose this because each of them is bringing in an aspect that we need to look at. The Roman number 3 has a fraction. We are differentiating a fraction. Now someone will say, teacher has only given us constants. But do not worry. Recall that we said we shall start by saying we let our y equal to 3 out of x squared. But remember, in indices, whenever a number is being divided by a given number and this number in the denominator has a power, if we move this number or value up, the power changes to either a negative or a positive, depending on the operator that is in front of the power. So for this case, our power to x or to the denominator is positive. When we take it up, it becomes a negative. So this will then become, so we shall first simplify it in a form where we can easily differentiate. So we shall get 3, we take our x to the power 2 up. So we shall have 3 times x. But we said initially the power was a positive 2. So when it goes up, it will become a negative 2. Is that okay? Now, when we get this, we can now proceed with our normal differentiation. So when we differentiate on the left hand side, we shall get dy dx. When we move on to differentiate on the right hand side, we say we shall multiply the power with the constant in front of the function. So we get negative 2 times 3, and the variable will reduce its power by 1. So we shall have x, the power negative 2 minus 1, like that. So when you multiply this side, we shall get negative 6, and negative 2 minus negative 1 you get negative 3. So we shall get x, the power negative 3. And therefore, you can leave it like this, or you can take it back in the form of a a fraction. So, assuming our question wanted it that way, we shall see how to take it back. So this as well is correct, you can end there. Or you will have a negative 6 divided by the x will come back down, but the power now was negative. When it comes down, it becomes a positive. And that will be our answer in that form. Or I said someone can leave it as negative 6 to the power negative 3. So these two are all correct for that case. So I've shown you how to differentiate a fraction. Now the fractions will change, but the concept does not change. Let's look at the last part of that example. Let's look at the last part of the example. We have Roman number 4. Roman number 4. And this one now has a square root sign. So what does this tell you? It tells you that for any number that will have a square root sign, be it a cube root or to the power, a quarter, all those mean the same thing. So similarly, you will first let y equal to root of x. Now, in indices, any number that we are getting a square root is the same as multiplied by the power half. So this is the same as y is equal to x to the power a half. So someone will say, why is now teacher bothering to change this? I am changing it because we need the other aspect of subtracting the power by 1. In this case, when we have a square root sign, we are not going to be able to figure out which power we are reducing by 1. So we first change it in terms of powers. So once you do that, we go back to our simple form method. So when you differentiate y, you get the y, the x, being equal to, what did we say? The power will move in front, or it multiplies with the function that we have on the right. So we have a half times x to the power a half. What did we say? You subtract the power by 1. So it will be a half minus 1. That's what we get. Now we shall have a half x. Now a half minus 1, what do you get? You have half an orange, remove 1, meaning you're going in a deficit. So if you're not quite sure, you can do it in a raw form. You will have a half minus 1 out of 1, which gives us 1. The LCM is 2. Then 2 divided by 2, you remain with 1. 1 times 1 is 1. Minus 2 divided by 1, 2. 2 times 1, 2. So we end up getting negative 1 out of 2. But you can put it in your calculator as well. Since we use scientific calculators, you can put a half minus 1 and it will give you a negative half. So the new power here is going to be a negative a half. The new power is going to be a negative a half. So that is our answer for that case. Some people can go on to simplify it further if the question requires. So these are our examples, and I hope they throw more light on that. So we shall take a quick break, and when we come back, we shall go ahead to look at more further differentiation, see how we differentiate a constant, and also how we differentiate sums and differences. This is Mbulamuko Secondary and Vocational School. Please subscribe and stay tuned for the next video. Thank you.